So let's continue with the amplifier models. So what we have here is the signal source Vs of t, and this is the resistance so RICI forms the input impedance, input resistance. Ri and Ci forms the input impedance of the amplifier. Okay, so Ri is the resistance and Ci is the input reactance or impedance of a capacitor. So total way is the combination of resistance and the capacitance. And the voltage amplifier model can be represented as the voltage that gets developed across this resistor or a capacitor is Vi of t, and this Vi of t gets multiplied by the amplifier gain to develop a voltage across this amplifier, and output resistance of this amplifier indicated by Ro, that is then final output voltage is delivered to the load. So this is now VL of t. Okay, this is VO of t right over here, and that's the voltage that gets developed across these resistance. So what to understand here is we take a look at that this much section up to this one is the voltage amplifier. All right, and then we have another section, let's say this section over here, that we call as a load section. Okay, and then we have this section which is of the source. Fine. So what is the question here is we are asked to calculate the gain of this network, which is the ratio of the load voltage with respect to time divided by the source voltage with respect to time. Okay, and we have to take the magnitude and which is this gain, total gain of this network, let's say AV. So this is, let's say, this total gain, and then we have phi, which is the angle of VL of t divided by Vs of t, and then we have to obtain the frequency response of this network. Basically, this is an amplifier with source and load connected to it. Okay, and this in between, this the model for the voltage amplifier. So the frequency response will be composed of magnitude with respect to frequency, how magnitude varies, how the gain varies actually, and how the phase varies with respect to frequency. So that's how we can obtain. So how to do that? We have to understand that we can write Vi of t, that would be that can be written as this Ri and Ci can be written as Zi, which is Ri 1 by j omega Ci, which is, this is the input impedance of capacitance, that's the resistance of a resistor. All right, so Zi times Vs of t divided by Zi plus Rs. Okay, and then this can be simplified further as Vi of t divided by Vs of t, which is Zi plus Rs. Okay, when we know that if the source impedance Rs is 0, we see that essentially Vi of t is equals to Vs of t. So what does that mean? The whole source voltage gets applied to the amplifier input, which is Vi of t, if the source resistance Rs is 0. Okay, right here. And similarly, we can write the expression for the output voltage, which is RL. This is a simple voltage division rule here. VL of t can be calculated as RL times Vi of t times A, which is output voltage, and RL plus RO. All right. We can also write this VL. So amplifier's gain would be VL of t divided by Vi of t times RL times A RL plus RO. Okay, so if RO is 0, amplifier's output resistance is 0, what we see here is that we see that this RL is 0. It means this whole voltage that gets developed across the output of amplifier that delivers to the load. Okay, so we can write this VL of t divided by Vi of t, which is the output of amplifier and the input of amplifier, that is equal to A for RO equals to 0. Fine. And finally, if we want to write the expression for VL of t divided by Vs of t, which is the total response, that is the output of this circuit divided by the input of this circuit. So we have these expressions. So what we can write here is in a simplified way, we can just write here. So we write VL of t, that is RL times A into Vi of t RL plus RO, and we just plug in the value of Vi of t, RL times A, and value of Vi of t is this expression right here. So Gi into Vs of t divided by RL plus R0, that's there, and we can write it like this. So this is there, and the Vi of t can be represented as Gi of t into Vs of t divided by Zi plus Rs, that is VL of t, and take the ratio of the gain voltages, A times Zi. This is RL plus RO, Zi plus Rs. Okay. So for the practical case, for the ideal case, for instance, if we see that here Rs is 0 and there is no source resistance, and amplifier has the 0 output impedance. Okay, RO is also 0. And in the case of Zi is Ri plus 1 by j omega c. Okay. So we see that Rs and Ro goes out, and this amplifier's voltage gain, that equals to A right over here, because Zi in the numerator and denominator gets cancelled. Okay, we can write this expression further. VL of t divided by Vs of t, and that can be written as RL times A, and plug in the value of Zi of t 1 by j omega ci divided by RL plus R0 Ri plus 1 by j omega ci, okay, Zi plus Rs actually. So this is Zi and plus Rs. So that's how we have this expression for the voltage gain. This is the expression for the total voltage gain of the network. Okay, so can we simplify it further? Yes, we see that RL times A, this is Ri plus 1 over j omega Ci, and this is RL in bracket Ri plus 1 by j omega Ci. So if Rs equals to 0 and Ro that equals to 0. Okay, so depends with that we have this cancellation, and what we see here is VL of t, Vs of t, that is approximately A. Okay, that is equal to A. But if these in a practical situation, these two conditions won't be there, so we'll definitely have a different value of gain A. Okay, and now for the expression, if we see that we write this in a sense that for the practical expression would be like this for the practical case. So now we can see that this voltage gain VL of t divided by Vs of t, this varies as a function of frequency. J omega Ci, okay, is the 1 over j omega Ci is the input reactance of this capacitor. And why this capacitor is coming into action? Because in the amplifier, this amplifier that we are talking about, this capacitance at the input terminals of the operational amplifier or simple any amplifier that comes from the discrete or integrated semiconductor devices such as BJT or MOSFET that we used to form an amplifier. So there are semiconductor junctions, and through these junctions, these capacitors comes into actions. All right, so we'll see that, explore that further when we go ahead. So for now, this is how the expression, and we can take this magnitude of this expression, VL of t divided by Vs of t. How to do that is basically one has to see. We can do is this is the expression for the total gain actually. Okay, this is the simplified gain. This is simplified after we take this assumption, and this is original, or say a practical case. All right. As a function of frequency, can we write it in a different way? For instance, can we write it this expression in terms of S variable, that is Vs of S, VL of S and Vs of S, and that would be written as RL times A divided by Ri divided by 1 plus Sc, because S is j omega. So this is Sci. Okay, so we are just replacing this j omega by the S variable. And similarly, in the denominator, we write RL plus RO, RI plus 1 over SCI plus RS. Okay, and we just write in terms of frequency J omega. So VL of J omega again, we are going back to the original equations. Okay, so that's how we see this expression. We can further simplify this to obtain the magnitude and the phase, but through these, once we have obtained this, these are basically, this function can be simulated with the circuit simulator to obtain the magnitude and the phase of this network. We'll see that later. All right.